Today's topic is rare earths. At the end of the 18th century, in a small quarry in the Swedish village of Turby, an army officer and amateur chemist found a black heavy rock that looked like nothing he had ever seen before. He called it terbium. He didn't know it, but he was holding a rare earth in his hands. The fuel for World War III, the key to artificial intelligence, and the secret behind every screen that lights up the faces of 8 billion people today. And for more than a century, these elements were treated as exiles on our periodic table. They were thrown into two lonely rows at the bottom of the chart. But chemistry is very ironic. What we call rare earths are in fact not rare at all. Neodymium, for example, is more common in the Earth's crust than gold. So the problem was never the existence of these metals, but rather the extraction of these rare earths. Unlike iron, which we can melt and shape, or oil, which you can pump and burn, rare earths are chemically stubborn. They bond to each other with great affinity. And to separate praseodymium from neodymium, for example, you don't just use heat. You have a battle of solvents, acids, and thousands of purification stages. It's a kind of modern alchemy. We've turned mountains of earth into grams of absolute purity. And the true importance of these elements only emerged from obscurity during the Manhattan Project. The need to purify uranium for the atomic bomb forced scientists to develop ion exchange separation techniques. And what was once a curiosity became a national security asset for the United States. During the 1950s and 60s, the world was analog, but it was about to become electronic. The advent of color television was the first major market test. Without europium, the red on screens was pale and lifeless. And suddenly, the Mountain Pass mine in California became the center of the technological universe. The United States held the monopoly. They had the technology, the extraction, and the market. It seemed like an unshakable dominance. For decades, the United States held 100% of the production of europium, the metal that gave the world color television. The vibrant red of the screens was not just an aesthetic choice, it was a sign of dominance. But American dominance was based on short-term market logic, and extraction at Mountain Pass was expensive, with regulations starting to tighten the noose. The separation of the elements released radioactive waste, and the cost of treating these effluents ate away at profit margins. The West was focused on the final product but neglected the infrastructure at the base of the pyramid. While the United States relaxed in its hegemony, a man in Beijing was thinking about something else. Deng Xiaoping, the architect of China's economic opening, had a geological understanding of geopolitics that his Western contemporaries ignored. In 1992, when he visited the Baotou mining complex in Inner Mongolia, he didn't just see dust and old machines. He saw a reserve army. And it was there that he uttered the phrase that still echoes in the corridors today. He wasn't just making a geological observation, he was laying out a 50-year master plan. And he said, "The Middle East has oil and China has rare earths." And this wasn't just a passing remark, it was the beginning of a predatory price war. China made a state decision. They were going to flood the global market with rare earths at prices below the cost of production. And they didn't care about immediate profit. The goal was to make mining anywhere else in the world economically unviable. And here you can see that the strategy was to dominate the value chain. It wasn't just about selling rare earths, but about controlling chemical refining and the manufacturing of components like supermagnets, forcing Western companies to move their factories into China in exchange for these materials. And the world only woke up to the weight of that statement in 2010, almost 20 years later, when China blocked exports to Japan due to a territorial dispute. It was then that the United States realized the prophecy had become reality. They were now technologically held hostage by Beijing. And the strategy worked with surgical precision. So between 1990 and 2000, the price of rare earths plummeted. Mountain Pass, unable to compete with Chinese prices and suffocated by environmental costs, was forced to shut its doors in 2002. The West celebrated the low cost of electronic components without realizing it was handing over the keys to its national security. China, on the other hand, didn't stop at mining. They implemented the policy of knowledge in exchange for market access. If a Western company wanted to use cheap rare earths, it had to build its factories in China. Thus, in less than 2 decades, China not only controlled the ore, but it captured the entire custody chain, from refining to the manufacturing of high-performance neodymium magnets. Now we can imagine the most advanced war machine in human history, a fighter jet. It is a jewel of stealth engineering capable of disappearing from radar and striking with surgical precision. But if we take apart an F-35, we'll find something a bit unsettling, because each unit contains about 417 kilograms of rare earth materials. In other words, neodymium is in the powerful magnets that move the flight control surfaces. Samarium cobalt is used in radar sensors and electronic warfare systems because it retains its magnetism at extreme temperatures where other materials would fail. Erbium is at the heart of fiber optic amplifiers, which allow the plane's brain to process data at the speed of light. And almost all of these kilos of critical minerals come directly or indirectly from supply chains controlled by China. But to understand why rare earths are a silent arsenal, we need to understand high-performance magnetism. Before the discovery of neodymium and iron-boron magnets in the 1980s, electric motors were bulky and heavy. Rare earth magnets enabled extreme miniaturization. Without them, cruise missiles would be too large to be maneuverable. Surveillance drones wouldn't have flight autonomy, or nuclear submarines would be detectable, since their engines would be much noisier. China not only extracts neodymium, it holds the patents and the know-how to forge these magnets, and that's what's important. When China threatens to restrict exports, it's not just cutting off rocks, it's shutting down the precision capability of Western weapons. And if Silicon Valley is the clean face of technology, Baotou in Inner Mongolia is its basement. Baotou is home to the largest rare earth mine in the world, Bayan Obo. What you see there is a scale of devastation that defies comprehension. To separate the elements, the ore is crushed and bathed in sulfuric and nitric acids. The result is a lake of toxic and radioactive waste stretching for kilometers in circumference. The soil around it is saturated with thorium and uranium. But China has accepted making this environmental sacrifice in the name of hegemony. When the West exported its factories to clean up its own countries, China imported the world's pollution in exchange for total control over the infrastructure of the future. The Pentagon classified rare earths as a level 1 security risk. China's 30-year strategy had finally delivered its checkmate. And we also have to talk about Brazil. Often confused with rare earths, niobium is a strategic cousin that Brazil controls with an iron grip. About 98% of the world's exploitable reserves are in Brazil, something even China envies. But there's a critical distinction. Niobium is a transition metal used to make steel lighter and stronger. Rare earths are electronics. Niobium is structure. However, Brazil has massive deposits of rare earths associated with phosphate and iron mines. So why isn't Brazil the new China? And the answer lies in the learning curve of refining. Extracting the ore is the easiest part. As we've seen, they're not rare. Separating them to 99% purity requires a chemical infrastructure that Brazil is still trying to build. So if Brazil managed to verticalize this production, moving from exporting mud to producing purified oxides, the balance of global power could experience a seismic shift. Another point is the battle for the Arctic. So as the polar ice caps melt, a new geological map is about to emerge from beneath the ice. Greenland has become the most coveted chessboard in the world, and it is estimated that the island contains some of the largest untapped deposits of rare earths and uranium on the planet. In 2019, the world laughed when the president suggested buying Greenland from Denmark. But for intelligence analysts, this wasn't just a joke, it was an act of strategic desperation. China had already infiltrated Greenland's economy through investments in mining, and the West realized that if China controls the Arctic, the encirclement of Western technology will be complete. Today, Greenland is a symbol of a new Cold War where the soldiers are geologists. We can also look to the deep sea. So when solid ground becomes politically impossible, we always look downwards. The bottom of the Pacific Ocean, specifically the Clarion-Clipperton Zone, is covered with polymetallic nodules. Rock potatoes rich in cobalt, nickel, and rare earths that took millions of years to form. The problem is that the environmental and technological cost is astronomical. We're talking about mining at a depth of 4,000 meters in an ecosystem we barely understand. The International Seabed Authority is at an impasse. Authorize mining to save the green economy, batteries or wind power, or ban it to save the oceans. And that's the environmental paradox of the 21st century. But if mining is dirty and politics are unstable, the solution might already be with us. Millions of old smartphones and computers contain precious grams of neodymium and dysprosium. Currently, less than 1% of rare earth elements are recycled globally. And why is that? Because it's cheaper to mine than to dismantle an iPhone. But science is always advancing, and we're developing bioleaching processes where bacteria are trained to eat the metal from circuit boards in a clean way. Apple and Tesla are investing heavily in disassembly robots to recover these materials. Recycling is no longer just an ecological choice, it's a survival strategy against the Chinese embargo. If we manage to create a circular economy for rare earths, China loses its power. And the billion-dollar question is, can we live without rare earths? Companies like BMW and Renault are already producing externally excited electric motors that don't use neodymium permanent magnets. Toyota is developing new alloys that reduce the use of lanthanum, but there's a cost. Motors without rare earths tend to be less efficient or heavier. In military aviation and space technology, where every gram counts, substitution is still a distant dream. So for now, the periodic table continues to dictate who rules the world. And often when we talk about artificial intelligence, we think of lines of code, algorithms, and the cloud. But the cloud also has a physical body, and that body is made of exotic metals. Silicon is the brain of all this, but rare earths are the nervous system and the sensors. We have NVIDIA chips that train ChatGPT and rely on capacitors and connectors that use tantalum and lanthanum to ensure electricity flows without noise or excessive heat loss. In precision sensors as well, in robotics and autonomous cars, they depend on lutetium and terbium. Lutetium is used in radiation detector crystals and high-precision lasers like LiDAR, which are the eyes that allow AI to map an environment in 3D. In addition, we have data storage. So as AI generates bytes of data, we need hard drives and magnetic memory. Ruthenium and gadolinium are essential for increasing magnetic density, allowing more information to be stored in ever smaller spaces. So the next great revolution in computing is not binary but quantum. And here, the dependence on rare earths becomes absolute. Quantum computers operate at temperatures close to absolute zero. Helium-3, which is a rare isotope, is used for cooling, but the quantum bits themselves often use rare earth ions, such as praseodymium and europium, trapped in crystals. And these elements have unique optical properties that allow quantum information to remain stable for longer. Whoever controls the supply of these purified isotopes will control the ability to break any encryption in the modern world. And besides looking down, we can also look up. So if Earth is at a geopolitical impasse, the answer might be in the sky. M-type asteroids, which are metallic, like the famous 16 Psyche, contain more precious metals and rare earth elements than the entire Earth's crust combined. It is estimated that the value of the metals in Psyche is over $10 quintillion. Even NASA and private companies like Astroforge are already testing technologies to refine metals in space. And why is that? Because bringing tons of rock back to Earth is inefficient. So the idea is to mine the asteroid and use the metal to build spacecraft and space stations right there in space. The moon also has deposits of potassium, rare earth elements, and phosphorus. The race to establish a permanent base at the moon's south pole, Artemis versus that Chinese program, is not just scientific, it's a race to claim the first gas station or mine outside of Earth. All this mining is still unfeasible today, but who knows, in the future we might already have space mining. And so, after decades of inertia, the Western world finally realized that naive globalization created existential vulnerabilities. We are witnessing the birth of the Mineral Security Partnership, led by the United States, which will include Australia, Canada, Japan, South Korea, and the European Union. And the goal is not just to mine, but to create a friendly supply network. And the idea is simple. Democratic countries should buy and process minerals among themselves, even if the cost is higher than the Chinese one. It's national security at the high price that countries are willing to pay. Australia has already become the largest producer outside of China, proving that the monopoly can be broken as long as there are subsidies and political will. And what about Brazil? Brazil reaches the end of this narrative at a historic crossroads. We have the second largest reserves of rare earths in the world, but our participation in the purified oxides market is still somewhat marginal. The case of niobium served as a lesson. Controlling the reserves is not the same as mastering the technology. And for Brazil, the future isn't about becoming the new China of mining, but about taking advantage of its clean energy matrix for refining. Rare earth processing consumes immense amounts of energy. And doing it with hydroelectric, wind, and solar power gives Brazil a carbon footprint advantage that China, which relies on coal, doesn't have. So if Brazil verticalizes production, creating magnets domestically, it will stop being a pawn on the board and become one of the kings of the new green economy. And as we come to the end of this video, we face a truth. The transition to a low-carbon economy, electric cars, wind energy, requires an unprecedented amount of mining. And to save the climate, we're digging ever deeper holes and using increasingly aggressive chemical processes. The technological sovereignty of the 21st century will be defined by whoever solves this problem. China won the first round because it accepted the mess, and the West will win the second round if it masters the circular economy. The real victory won't go to whoever mines the most, but to whoever can keep the same neodymium atom in circulation for 100 years through molecular recycling. So the phrase from 92 was a warning that the world took 20 years to hear and another 10 to react to. China used rare earths to build its middle class and its military strength, but the Chinese monopoly is starting to erode. In 2010, China controlled 95% of production. By 2024, that number had dropped to about 70% and keeps falling. So other countries are learning Beijing's lessons. The era of absolute dependence is coming to an end. No one will be totally self-sufficient, but no one will go back to being completely hostage either. So the story of rare earths is, ultimately, the story of human curiosity turned into both weapon and tool. From a black stone in Sweden to the engine of a stealth fighter jet, these elements have shaped the modern world. The prophecy has been fulfilled, but the script for the future is still being written, atom by atom, in the mines, in the laboratories, and in the depths of space.